Professor Brocato teaches the École Nationale Supérieure d'Architecture. I'm sorry for the for the French pronunciation, ENSA, in Paris-Malaquais, and at École des Ponts Paris-Tech. He is the director of the ENSA Paris-Malaquais Geometry Structure Architecture Laboratory, and he is president of the Department of Digital Matters in the same school. His research is focused on the interaction between shape and composition of structures, with particular emphasis to discontinuous and entangled systems. Today, Professor Brocato will give us a lecture on an all-time challenge for designers and builders of vaults made of monolithic blocks. He will show how stereotomy, which is the art of stone cutting, can play a fundamental and complex role in the statics of these structures. The title of his presentation is Stereoplexy, and I guess he can explain better than me what this word means. Welcome, Professor Brocato, the floor is yours.
Thank you very much. Thank you, first of all, for inviting me, and then also for letting us share this very nice moment today. So yes, the title of my talk is Stereoplexy, and I will take most of the time of the talk to explain why I choose this title. And I like, first of all, so I'll show some pictures and then tell a little bit about the mechanics, that is what I understand of those structures. Now, first of all, as a forward, I will start with a word of Professor Majewski this morning. There, a stone has three meanings. He was mentioning something that is that I try to summarize also in a few slides. That the stone, the design of the stone is at the same time the design of the wall, so it contains the overall geometry. It is the design of the statics of the system, and it is also an artistic matter in the sense that all those shapes contribute to the beauty of the building, not only to its statics. So, in a sense, this is at the same time the heritage and the burden of what we name stereotomy. Stereotomy was a discipline born after the Renaissance, mainly in France and Spain, and as the definition is the art of cutting stones, so that each individual stone contribute to the assembly and make the wall a structure. Now, the motivation in the origin was simply to provide proper geometric rules for the assembly. And then, as the understanding of the structures of that period was based on two simple tools, that were the inclined plane and the inverted catenary, then the stereotomy became also, and in this sense I say a burden, became also a monopoly on the way to watch stone structures, that is the inverted chain rule. What is important in stereotomy is that it anticipated the idea that information can flow continuously from the detail to the wall and back, and that from fabrication to assembly. So in this sense, the sentence of Professor Majewski, a stone has three meanings, is what is important to us in stereotomy. On the other way, the fact that the law of inverted chain became a sort of law to be respected by all stone structure. This is something I would like to pass on, in a sense, to go beyond this sentence. So this is why I say, instead of watching at the cutting issue, let us talk of the weaving issue. And so stereotomy became stereoplexy. Plexi is the Greek word for weaving. I will start with a gallery because I think it's easier for you to understand what I'm talking about. This is a stone dome we built in Qatar, 6 meters span. It's a geodesic dome with a kind of particular assembly I will talk about as Abbe design of dome. So this is one example. This is another example of interlocking domes, much smaller. It's presentation was done in Salon du Louvre in Paris, just 1 meter span, but it's built with the same technique. This is a saddle vault, a Bohemian saddle, so in my knowledge, maybe the first and the only so far stone structures that does not have a synclastic shape, but anticlastic shape. And those are built with the same techniques as walls that could be transported, lifted, and that can work under wind and other loads. So again, you understand that the multiplicity of loading that can be withstood by those structures testify for the fact that they are not only or simply inverted catenary systems. Here is again interlocked wall makes this time with cubes. It's a very old known assembly of cubes that can be found in treaties of the 17th century also, but that has been recently studied extensively for the high resiliency that the system can have under impact, especially. And now another dome. This time it is a gyroid shape, and the interlocking is made by following a Chebyshev net on the wall. This is on the dome. Sorry, this is a 9 meter span. Was built in Jericho in Palestine. Here are some details, and this is from below. This is experiences on carved joints. This is the dry stack tower that was built in Victoria and Albert Museum in London and then rebuilt in an exposition in Dubai. And in the end, it is today in the Crimson Valley between Jerusalem and Bethlehem, very famous at the time of this exposition because of the Friday prayers that were made there. Those are the two architects that conceived the tower, Youssef and Elias Anastas, in Victoria and Albert Museum. Some more and different work on stone. This is a sawtooth beam where a single bar make the system work as a beam. You can see that the end has no thrust. The bar is not a simple tie, but is bonded to the stone. So the system works rather like a concrete, reinforced concrete beam that like an arch with the annihilated tension. And following this path and some experiences that we made after, this is an anti-seismic structure, a 6x6 building built in French territory in Israel, the Benedictine Abbey of Abu Ghosh, and the roof is made with what is called a bay vault, which I will explain a little later, and it is reinforced with steel, and the columns also only stone and steel, and the whole system is compliant to the Italian code. Notice that Palestine doesn't have its own code for seismic rules. So this is the outside of the same building. And going to the working of ties or reinforcement bars into those structures, this is a Monge helicoid, so it's a real surface with several blocks. Unfortunately, those are not stones but concrete. This is rather a sort of an exception in my talk, but what is important here is that you have those complex joints that are linked with bars. And here, the last structure I want to show is a bench that was given to, taken by Victoria and Albert Museum as a permanent collection. And here it is, the place you find it in the museum if you go there since 2019, last February actually. February 2019, sorry. So now that I've shown some pictures, I can tell you why I think the inverted catenary system or thought is too much a limitation for them. This is the originally drawing from Fraisier that show the invention of Joseph Abbé at the end of the 17th century. You can see here this particular kind of assembly. And here are some tests. Maybe very few structures were built in the 19th century, only 2 actually in Spain with this system. And then at the beginning of the year 2000, some experiments were started in my school before I arrived actually. And so if we do some limit analysis on those structures, you resume here what you do. You assume, of course, you know the equilibrium configuration. Stones are rigid bodies and are of infinite resistance. Joints are unilateral, and the forces that are transmitted through them are contained in some bounded convex domain. The load is given, and then you work on the reactions that becomes the parameters, so as to find a kind of set of equilibrium forces, internal forces that withstand the external load. And if you find one system of of this kind, then you say that the valve is stable, and you can in most cases, of course, the system is a little more complex, but in the end, you get out with a kind of inverted fishnet. And so this network of truss lines became a paradigm to understand the structure. Now, I want to show what happens with usual flat valves, so not Abbe valves. So this is a barrel valve. Those are taken from Rondelet. This is a barrel valve. This is those are domes, and this is a cross barrel valve. And so in all those cases, you have these red lines that show how the loading goes to the supports. The red lines are orthogonal to the main truss, let's say. So those valves can be named after the shape of the Dupin indicatrice of their fishnet, in a sense, and they can be talked as parabolic or elliptic. Now, in the sense that here you have an elliptic shape or a parabolic shape that represent the inverted chain of the system. Now, if you look at Abbe valves, this is not so. So this is the example of the fishnet or the truss network for an elliptic flat valve. So, well, something that you can well understand with the truss, which is higher or lower, and you have this shape that appear. But if you do that with a Abbe valve, that you cannot use a single net. You must use 2 nets linked with struts. So you understand that the struts that are compressed items in the net represent the tension in the stones. And here I have some 3D. I wanted to have an animation, but it didn't work. So I put just some image from that. You see the struts are red. This is compression in the inverted system. So it is tension in the real system. And you see the blue nets that interweave each other that represent the compression in the stones. Second particular issue that is proper of Abbe system is that they can withstand inversion of the load. So this is the typical pattern of self-weight against thrust. And you can see classical valves, of course, you can only have positive self-weight, and Abbe valves where you can have negative self-weight. So they can work in both sides, in both ways. This is why you can do walls with them. Now, if we go a little further and we try to understand what happens in mechanics, so how does it work, then you can assume blocks be anisotropic elastic bodies. You can have particular more Coulomb law on the joints, and do a step-by-step computation, like you can see here, the simulation of a 13th century flat arch in Beauvais. And what happens is that if you look at the stones and you try to look at the quotas of elastic energy, so you assume a stone with kind of a beam, and you see the elastic energy that is in the stone as due to the bending moment, as due to the shear forces, as due to the normal force, and etc. You see that the highest, much higher than the other quota of elastic energy is in bending. So stones actually work in those systems as banded items, not as struts. So the inverted catenary system, if it tells something that is not really connected with the real elastic energy that is present in the system. And this is something else that you can see if you lock all the contact on the left, and if you leave the contact being possibly open on the right, you see how the elastic energy locates in the structure, rather in the center, in the case of a simple elastic grid without joints, or on the boundary, in the case of an elastic grid with opening joints. This is what happens. So in reality, when the different loading condition happens, when, for instance, this is the rising condition, transportation forces orthogonal to the plane. This is wind or horizontal forces on the panel, and this is vertical forces on the panel. You can see that, of course, the panel is able to react in many different ways. And so it is an element that can be a part of a structure much more complete in a sense than a simple valve. And for the case of domes, I want to show another couple of pictures where you have here all the joints, and you see some of them that are open, some that remain closed. So you understand that there is actually a pattern of opening and closing joint that makes the system work. And when you look at stone by stone, you can see that each stone has, this is von Mises stresses in the stone, and you can see that the stone is basically bended. This is to understand also the effect of flexibility, so the difference between a model with rigid blocks and a model with elastic blocks. Lighter colors represent rigid blocks, and blue darker colors represent flexible blocks. Those are computation made on a sawtooth loading on the previously shown dome, this one. And you can, and this is the top deflection, and you can see that there is a neat difference between assuming that the stone are not flexible and considering them flexible. This is, my understanding, this is because, of course, this is a statically undeterminate system, and the way that loads go to the boundary depends on the flexibility, and it cannot be, let's say, this dependence cannot be in general not considered. Okay, so I think I used the time, so I go to the conclusion that is a simple picture and the sentence of Auguste Perret: architecture is what makes nice ruins. And those are the name of the co-authors of the work that I've shown. Thank you for your attention.
Okay, thank you, Professor Brocato. So it seems very interesting, this work, because it seems you are building some walls that are actually flat, but we know that flat walls are have a very high thrust on the supports, while for what I understood, this kind of walls is working more in the flexural behavior. And so then how is this influencing the thrust on the support?
Yes, there is a, in considering thanks to the shape, the thrust on the support is much reduced. And we have made some analysis to understand how the shape of the blocks could affect the thrust, and if there is such an effect. If you read the treatise of the 18th century, there is a long debate about the wedge effect and the catenary effect, which one is dominant, for instance, in a flat arch. And actually, you understand that there was something missing in their reflection. That is, they were missing the knowledge of mechanics of elasticity, which wasn't there. This is a bubble diagram that shows compared computations on.
Excuse, we cannot see the diagram.
Oh, I'm sorry. Yes, sure.
Because you're sharing this.
Yeah, I'm sharing not the screen, but one document.
Okay.
So, okay, now I think you see the diagram.
Okay,
and,
thank you.
So this is a set of different instances of the same vault with two parameters, and an angle, alpha angle is what we call the splice angle, that is the shape of the stone, and the phi angle is the angle that allows out to be the inexorate, the shape actually of the frame. And well, the color, the gray or white, depends on the computation. This is rather a numerical issue. But what you can see is that this is the maximum thrust at one stone on the boundary, and you can see that it doesn't change a lot from one end to the other of the diagram. That means that actually there is not an enormous effect of the angle. As soon as there is an angle, in a sense, a reasonable angle, because of course you cannot do too much tight angles in stones, because then they break. So when you are in the range of angle that you are supposed to be able to build, actually, then there is not an important effect. The thrust is anyway reduced, and there is not a very important change in the thrust by changing this angle.
Okay, thank you. Just another question, if there are not from, yes, I give the priority to Stefano, which wants to ask us question.
Thank you, Maurizio.
Thank you.
Very interesting. I didn't know anything about this kind of flat vaults before. I was wondering if, I was thinking about the behavior of an arch, in which you have the bending effect with respect to the truss. It also is dependent on the span to the 8 ratio. Is that in this kind of structures a geometric ratio that regulates the effect of the bending stiffness with respect to the, let's say, axial or membrane stiffness? If you see it in the large of the 2D structure, that regulates the behavior of the structure, that is from a vault to a plate or something like this. I don't know if the question is clear.
Yes, clear. And we actually did a parametric study on flat valves to understand when they behave as vault and when they behave as what we can say, I don't know, flat valves of the Abbey kind. And this is one part of the answer is displayed by this computation. You can see that whatever, this is the parameters here, the phi parameters, is the splice angle. You pass from one flat valve like this to one like this, and you can see that there is always a dominance of bending. In a sense, I must say that when bending takes place in a structure, then it dominates. This is a little bit the reason why what Professor Moyer PhD was saying this morning. You get two words that are easy to understand and something in between that is more confused in a sense. Well, this something in between which is more confused dominates as soon as possible the other two. So to be a pure cathedral in a sense is difficult. To be something in between, it's more natural. And so you see that in the end, as soon as you authorize by the splice angle or authorize bending to appear, then it dominates. And another question about geometry can be shown in this picture, maybe, yeah, this one. This is the equivalent of the fishnet for the Abbey valve. You can see that you cannot think of a single fishnet. So like this is a standard parabol elliptic flat valve. So you can imagine this inverted fishnet, and it's quite, I mean, intuitive today for engineering and architecture to understand that. And so it's a single net of forces. And here you need to consider two nets because you have phases, contact phases that actually cross each other in direction. And so the forces that are basically orthogonal to the phase, or at least within a certain angle to them, they go down or they go up depending on the direction you impose to the phase and not depending on nature in a sense. I mean, you force nature to do that. This is why I like so much this sentence this morning. In a stone, there is three things. Yeah, you actually, by choosing the shape of the stone, you modify the behavior of the wall system. And so then this geometric ratio is in a sense rather in the local stuff, is it here, is the geometric, you see here the line of thrust, it's out of the vault, but the resultant is in the joint. So this is a force passing from one block to the other. It is in the joint, so this is stable, but then it is equilibrated with another force which is there, which is in the other joint, stable also, and the two of them have a resultant that is out of the thickness of the vault. So this is why you cannot think the vault as an inverted catenary, because if you do so, then you have to assume to have a kind of virtual thickness that is higher than the real one because of the wedge effect.
Thank you, very
I
interesting.
hope it's clear, but well.
Okay, thank you, Professor Brocato.